All right. Hi. Slightly reduced team. What's that? Yeah, this is Pratchett. This is a whistle. It's for a dog. He's not a dog, so it's a little bit big. But it's so we can find him if he gets away. So I guess I'll start that again if I need it. Oh dear. Yeah, yeah, he doesn't really escape, but he's let me see if this comes back. Maybe video was too much. So exciting. All right. I'll fix that up in a. Oh, that's good. All right. I think that's working. Okay, let's go. So that's what I want. All right. I realize it's a little hard to see. Control C plus. This is wow, that's really, oh, that was really strange. Okay, sorry. All right, come on. I think that is just behaving terribly. All right, I'll bring it back up if I need it. Okay, so I was going to show you a couple of things. So it's Tuesday. We've done all that stuff. You know, sometimes I will show something interesting. Let me see if it's possible here. So this is an excellent new study. Look at this excellent science here. We're going to be talking a little bit about animals, so about how fast they can run, but this is fine work. Tardigrades, right? So that's one of our mascots is a tardigrade for our mass mutual connection, right? All sorts of good things, right? They can survive whatever, fire, incredible cold, blah, blah, blah. Water bears. But this is important knowledge. It's great. PNAS. All right, thank you, PNAS. Okay. So if you want to study tardigrade, you know, gait is incredibly interesting. There's an old, I was going to bring that paper by Strogatz and Ian Stewart, I think, on just all the different types of gaits and how they shift. You know, they're sort of famously horses, but elephants are like a four-knee situation. Anyway. All right, and we're this odd thing that runs around on 2 feet, sort of. Barefoot running, by the way, is the cure for everything. So, all right. Okay, madness from me. What else? Teams, these are just little housekeeping things. The teams, let me get teams without exploding. I'll try to talk a little bit louder. Come on. I don't know where it is. Come on, teams. The excitement of teams. Thank you, Microsoft. I think it's here. Yeah. So we'll get to these. So now it's not very obvious, but up here there's the instructions are just embedded from the website. So they're sort of, if you just stay within Teams, it's here. I guess, you know, right, so there's an assignment due this week. We'll talk about some of the things you need for it today. And this is just a little note, right? So it's 11:59 on Friday. It's just hand it in on Friday. It doesn't mean hand it in at 11:58, although if that becomes a problem for you psychologically, then maybe we need to just give it another time, right? So that you don't explode. So things are negotiable, but we're going to go with this for a while. But the idea is it's just on Friday, and so you can move that in according to what else is going on in your existences. Because I understand you do other things, right? Yeah. And I know professors don't behave like that. All right, so what else is in there? Yes, okay. Maybe I said this, but yeah, contact is through Teams, so please do that. You can contact me or Michael. Michael will help a lot. And what else? Okay, good. All right, so I thought we would just charge ahead, really. So let's do that. Restrain myself from too much nonsense. Acro read, you bad thing. All right, so we got to this piece, and I think I can do it. Right. Again, I just want to quickly go back. So we're kind of in this biology section, and this is, right, so this is the scaling of cancer rates, which, you know, profoundly important thing to figure out. And I think I don't think this has been understood, right? Like why the scaling is roughly 2/3, why it's rolling over. Anyway, so we're just sort of stitching through certain kinds of scalings that have been observed in biology. So here's a really important one: how fast can something run? And this is seemingly true, independent of whether organisms are in fluids, aquatic, or land-based, or in the air. So we have these sort of three big spaces that we move through. And of course, two of them have a 3D kind of existence, and we're very 2D organisms. We get excited about people jumping 2 meters or something in the Olympics, but it's pretty embarrassing, really. Our swimming is something that also, Australians great at swimming. We think it's fantastic, but it's pretty. If you walk past an incredible champion swimmer, you can just sort of walk next to them like this. I mean, they're going as fast as they can. It's cool, but we're not that great at it compared to the fish things, which the other day I was swimming in the lake, and you don't see many fish in the lake, right? You occasionally see some biggish kind of ones. And but I was swimming, and I looked down, and just below me was a ribbon. And I am terrified of snakes, right? Because it's just what happens if you're in Australia. Everything is poisonous, and it's true. All the snakes are poisonous. The little ones are poisonous. They're all poisonous. Lots of stories of snakes. But it was a yellow ribbon, and it was kind of back here, and I instantly sort of kicked, and of course it took off, and then I swam very fast. But I think it was an American eel. I think they're somewhat uncommon. The one to worry about is the lamprey, which is basically a horror, like it's a total horror movie thing with Jaws that does that. Anyway, mostly okay. Not so many sharks, although maybe in your mind you can think about sharks. All right, so point is, we're in a lot of trouble in the water if something bad comes for us. Okay. Again, many stories of sharks in Australia. So this is what's going on here. This is not, I've shown you a lot of scaling laws, right? This is still a scaling law, but it's been restructured, so it's the maximum speed something can go at. And of course, you can see, what do we got? 22 orders of magnitude here in mass. This is in mass. And so divided by the length scale, the sort of height or whatever the sort of dominant length is of the organism. And so that's pretty much a constant, right? So that's the point. This is a constant. So in terms of scaling, the maximum velocity is scaling like L to the power of 1. And so this is a 2015 paper. This is relatively new. And as I said, 22 orders of magnitude, which is roughly 7, 3 times 7 is 21, 7 orders of magnitude for length. So in terms of, if you had them all kind of stacked like this, you'd be going through 7 orders of magnitude, which is a long way, right? We're not good at understanding. And we'll come back to this again. Again, we're pretty terrible at sort of intuiting these. Well, yes and no. Okay, very small, very big. So we're getting up to blue whales and so on. But you do see this kind of, there's a roof here, right? Yeah. So there's a bit of a ceiling that's, there's a ceiling in this sense, and there's some real fluctuations here. This is 2 orders of magnitude, but broadly, yes. But there is a ceiling here. So and this is an assignment 2 question to kind of, get this scaling to pop out. So you can argue for why this might be true. And of course, it's just maximum speed. This is not, there are lots of speeds that you have depending on how far you're going. If you don't know how far you're going, that's going to be a different thing again. And Gates gives certain kinds of speeds for free, right? And we had those results for humans in running and swimming. There's no real flying in the Olympics, is there? No flappy. All right. Okay, so this is a paper from just a few years after that addresses this issue really here, right? And so and I can't remember the extent that paper sort of acknowledged it, but here's everything sort of pulled out in these 3 different categories, and we have, so again, right, so birds, again, some of these scales aren't the best, but so flying things, right, which includes some mammals, of course, bats are in here as well. I think albatrosses are your biggest flying birds, and then of course we have Struthious birds, ostrich and so on, right? They're big units that have given up on the flying part. But they fit into terrestrial running machines, right? The penguin, right? Some crossover teams here, right? The penguin, which has decided it's a fish. Yes?
On that last graph, would you say it would be medium quality or high quality scaling? Because
Yeah.
Because the y-axis was normalized, you said it was 7 orders of magnitude in length, but that's normalized to like 1.
Yeah, right. So this is a nice thing to do, but if we really did plot it like this, we'd just have a nice straight line. And the thing you're not really measuring this, right? This is messed around with, I mean, in the simplest way, but you're going out and you're scaring your, you know, octopus or whatever, and then measuring its length, and then you're going over to an elephant. It's a difficult, I mean, I don't know, of course this is from literature, but you can imagine the graduate student who had to do all of these things, you know. Like if you go up behind a frog, right, or a cricket or something, and go beep, they go jump. So someone had to do all those things, and of course a little bit of a measuring tape, right? So that's what you would measure, and that's okay, yeah. Sometimes it's good. It's a good question. Like sometimes these things are a little sketchy. We'll see some bad ones again, but no, I think this is good because the real things you're measuring really do vary over those orders of magnitude, yeah. And then this is one way to present it. And they do, you know, in terms of graphics, you know, not bad for scientists, right? This is a little bit of charm added to it. I mean, as they should. Okay, so flying, running, swimming, right? So this is speed. So this is, right, to your point, this is now just speed, right? We're not going to divide it by anything because this is much more helpful to see this. And again, orders of magnitude, speed is going here, running, right, and swimming. And there's some slight differences in those scalings, which may be interesting. But the big thing is that they're finding in here is this rollover. And so we're getting out of things like elephants, which should, in principle, you know, be almost an order of magnitude faster than what is this, a lion, perhaps, right, in terms of given their size. But this is something you look for in scaling. There's going to be a breakdown at the ends of scaling. It doesn't seem to be the case down here. It looks like we're down to some pretty small things. What breaks down here is there are no organisms below some typical scale. So for mammals, it's like 2 or 3 grams, something like that. We don't have small mammals. I don't know what the smallest butterfly is. I was thinking about that the other day. It's a sampling problem. You know, I'm seeing the wanderer butterflies, which we used to get in Australia as well, a little bit. I'm like, are there tiny butterflies? Anyway, there might be. I mean, it's surprising how small mammals can be, right? They're ridiculous, tiny little shrewing it up. Okay, so why is that? And so their argument is, well, they've got the stuff, they've got all the energy in there, but it's about how because this is anaerobic, right? This is your maximum speed is based on your anaerobic capacity, right? And we talked about this. The 800 is kind of a nasty distance, right? It's in between for running for humans, and 400 you can do the whole thing, right? You can burn the whole way, but it's pretty awful, right? The last 100 is in the prey category. But you know, if you're an elephant getting it going, you don't reach the hypothetical maximum speed that the scaling would suggest, right? And so there are a few things here. Maybe I don't have to go into too much, but it's here's their sort of, you know, his time. This is the mouse. So a graduate student lets a mouse go and says something scary to the mouse. Is that a porcupine? Let's call it a porcupine. So it's a porcupine and maybe a wolf and then an elephant. And then, or as my daughter used to say, a woofer. So this is, you know, so they pretty quickly get up there. But here's the elephant just, you know, building up right, it's a diesel engine, just getting it going. And then this is there's a scaling for the acceleration time, right? So this is body mass. They take longer to accelerate. And then putting those things together, you get this story, right? So that the mouse quickly gets up to its maximum speed is gone. And I grew up with mouse plagues, which you may have read about in Australia now. There were a couple when I was a kid, just unbelievable disaster. So mice can run very fast and they can get to that speed instantly, basically. Porcupine, I'm going to call it a porcupine, which I saw the other day. They can get up to some speed pretty quickly. You know, there's a little time in here, and the wolf and so on. And then the elephant is going, but it's run out of its energy that it's got available in an anaerobic sense. So it plateaus more quickly, and in fact is slower than smaller organisms. So, and then they have a little bit of a game with this story. They threw some dinosaurs in there to really, you know, sell it. But it's this kind of, you know, this isn't a perfect thing, but there's just a sort of typical idea. There's a maximum they can get to, and then there's a decay as it gets towards it, right? So if this is really small, then they can go boom, get there really fast. And it's going to be longer and longer. It's going to be K is going to be yeah, right. Okay, and then there's some sort of dubious scaling laws for these pieces, right? There's actually a scaling law for that factor, the K up here, this little time factor, and then for how much time it takes you to deplete your energy. So humans, it's sort of 90 seconds, right? And then you're gassed. And then if you rest for a few minutes, it rebuilds, and then you can go again, right? So, all right. So if you play around with these, you've got a bunch of little scalings, and then you can kind of get this story that the maximum is actually going to have some power in here and a power in here, and it's not going to really be right. So in principle, if you look at this thing, so okay, with enough time gets the maximum velocity, but actually putting these pieces in here, there's some scaling for the energy you have and the time it takes to deplete that energy. All right. So that's a nice, it seems, and you look at some of these things they fall apart, this seems to be a good bit of work recently for allometry. Okay. Yeah. All right, so let's move to other pieces. So biology, with all of this, I'm trying to give you a series of examples of scaling, just to sort of, this is the wide world of scaling, or whatever it is, something like that, a menagerie of scaling. And so we've gone through biology now, and there are, of course, more things. We're going to have some stuff in sort of physical, mechanical systems, people, money. I won't go on about that too much. I'll just sort of have one XKCD slide. Language has fantastic scaling. We'll talk about that more. And then these sort of technological things. Some really, and the terrorist behavior is in here, and how to Moore's law and all sorts of stuff. Okay, so yeah, engines, right? So this is horsepower, and of course those are different technologies being built over hundreds of years. And so this is brake horsepower, which is a particular measure of horsepower. So that, in terms of the engine, this is engine mass down here. It might be hard to see. That's, again, kilograms. What do we got? This is 6 orders of magnitude. So really 2 orders of magnitude in size, right? So the machines are getting bigger by, a factor of 100, which is in length scale. So that's just to get that right. That's a lot. And then weight is going to be, presuming density scale is the same way, or is constant. The mass is a huge differential here. So this is a little bit more like the animal story, right? So or it's about power, but it's something that's proportional to the whole thing in terms of mass. But the RPMs that you use for it tend to decrease at the same time. So the argument for that one I do not have here, but that's an interesting thing. This is something that's just, some of them are built on principle. Mechanical engineers did something or whatever, but sometimes it's just a result of the history of people making things. So making nails, you want your nail to function, but you don't want to use too much mass, right? You don't want to use too much material. You don't want it to buckle. You don't want it to break the wood, whatever you're doing, right? So there's some reasons you want a nail that's this, you decide you want to nail this long, and then you have to figure out kind of how wide it is. You have to machine it. So over a lot of time, right nails have been produced, and no one, I think, was guiding this, but it turns out this is the nail length, and this is diameter. And the diameter, this is an allometric scaling, so the diameter and length, if it was just normal dimensional scaling, they should be scaling like each other, right? That would be slope 1, right? This is length in inches, this is length in inches. They should have that scaling. But in fact, it's 2/3. So the diameter is, as length grows, the diameter is not growing as fast, right, as the length. So these are becoming, if we took this one and rescaled the length down, it would be thinner than this one. So it's not isometric, it's allometric. And then you always want to start putting things together. So if you see this plot, you're okay. Oh, all right. That could be interesting. So length, I try to turn all notifications off on everything. My God, I'm sure I've missed yeah. But anyway, length d squared is going to be proportional to volume. So that's right. If we put these two things together, I guess we can do it. I think. Do I have it on the next page? Maybe I do. So it would give you that the diameter is proportional to mass. Mass and volume are going to scale the same way, right? So diameter is proportional to mass to the 2/3, because we need diameter squared to get the cross-sectional area, right? So like pi r squared, to get an estimate of the volume. So it's going to be pi r squared, but really just r squared or d squared. It doesn't matter about the constants, times length. And so let's see if this works, right? So this will be 2 of these squared is going to be 4 to the power of 7, and then we have a 3 to the power of 7 left over. And so the 3/7 and the 2/7 go together to give us that 2/3 scaling. Let me argue that a little bit. Right, I said this piece. So that's sort of, you think, oh, if you're a physicist, sometimes you think that's a 3-dimensional volume thing, but this is weird, right? These are sevenths now. That's a bit odd. So what's the argument for this? This is a bit strange. And we want to tie things usually to mass, like we did for biology. So while that's a reasonable thing to show, this is really what you'd want. Diameter is proportional mass to 2/3, length is proportional mass to 3/7. They're peculiar. The 7 is peculiar. That's an odd one. So one argument for it is this: it's a buckling instability. So you're going to make a nail. It needs to be so long. You will make it as thin as possible because you don't want to waste too much. You also want it to, work. Right? If it's too wide, you can't nail it in. So you'll make it thin, so it will go in, but you don't want to get to a point where it will easily buckle. Right? So this, we're not going to drive this. It comes from a mechanical, civil engineering kind of world. And so columns buckle under a load, and it's going to turn out to be proportional d to the 4 of L squared. So that bit on the top, you can think of as cross-sectional area squared, and then length squared on the bottom. So the load that's required, right? So the longer it is, right? It decreases this thing with a factor of a power of 2. So that makes it easier to buckle. That makes sense, right? So if you just stretch something or you double its length, the load is going to be a quarter. But you get a huge return for increasing the diameter, right, in terms of strengthening it up. So then there's sort of these are these little arguments, and they may or may not be, I'm just showing you one. So you've got to drive this nail in, and then the resistance is going to be proportional to the circumference. That's sort of the argument. And then you'd want to have these things being roughly matched, right? So the load that at buckling, that kind of edge for buckling, you want that to be at a point where so that the resistance of of actually nailing it in kind of matches. So that's this little just so argument. If you just play around with this a little bit, you see there's a d cubed, right? If we divide that through, so d cubed is proportional to L squared. So d is proportional to L to the 2/3, which is the observed story. So Galileo made this argument apparently, and Euler. So there's some interesting characters who have thought about these things back when math cared about reality. Okay, so McMahon I mentioned earlier. McMahon is one of the authors of the coffee table book, and did some famous work. This is a bit funny. It's a bit of a funny paper in Science, 1973. Okay, because he has animals made out of cylinders. So it doesn't really seem that our limbs scale like that. Anyway, so that's an observed one, and there's a little argument for it. This is a similar kind of game where you have a few results. In this case from fluid mechanics, right? What's the drag, on a shape moving through a fluid as a function of velocity and its surface area and so on. So those things you've given, and you play around with some pieces. How many people are in the boat, the weight, and all those things, and you can get out this, this rather weak scaling. This is very weak again. This is a power of a ninth is the claim, right? So, do I have it there? No. Yeah. So, yeah, the 1/9 is up the top. Sorry. So speed is proportional to the number of rows of 1/9. So it's not a constant, which is 0, but it's very, very weakly above that. And usually when you've got this, 0.11, you would think if you measured that, you'd be like, well, maybe it's 0 and I've messed up. And again, there's only, this is 1 to 8. It's not even an order of magnitude. But Anyway, it's one of those things where there's weak observation and then there's a theoretical argument for it. But that's something to play around with. Okay. So more physics. All right. So here are some other there's scaling everywhere, and we'll get to the great Buckingham Pie Theorem in a minute. Right. So these are quite famous. So Coulomb's law and law of gravity. As I understand, I have a tarot card somewhere about this too. That I believe so in Newton's notes, and Newton, who was pretty much a crackpot, right? Like he spent a lot of his time thinking about. I don't know. Didn't he do all sorts of weird astrology things and so on? Yes. And anyway, good for him. And then went to work for money. So he basically went to Wall Street when he was 40. So, but I think in his notes he has R cubed and this he's just playing around with, right? Maybe even on the top, which is odd. But the R squared, has a story, right? It's the shell. It's the surface area of a growing sphere, right? So if you've got a point, the sun, and as you go out from it, this gravity is pretty strange, right? And we'll talk about gravity again later on. But the idea that it diminishes in this uniform way is kind of reasonable, right? So it doesn't have to be that way, but it sort of fits. So if you multiply this by the cross section, the surface area of a sphere of length r, then these r squareds balance. So it's diminishing. Right, gravity is weaker the further you get away from something by this 1 over r squared, but it's overall it's all still there. Right. Physicists have some work to do yet. Okay, so that's sort of reasonable. And so we see the square here, right? We think of dimensions. It's a 2, and it's really d minus 1, where that's 3 minus 1, and that gives you a 2, right? So the d is from 3 dimensions. We're talking about a 3-dimensional space. And there is an equivalent one, which I'll show you later on, that was noticed by Zipf and others even in the 40s. It's not true at all for everything that humans do, but there is a number of kind of gravitational stories that work where this is population of a city, population of another city, and this is the distance between them. And instead of distance squared, it's just distance to the 1, because we live essentially in 2 dimensions. And in that case, then this will be d equals 2 minus 1, 2 minus 1, which is 1. So it's the same, the gravity law of human behavior. So that, it's espoused. There are examples of where it holds up, but it's not true for everything. Usual game for scientists, right? You come up with something you think is true everywhere. Then everyone has lots of fights about that, and then you're like, well, there's some limit. Okay, so that's the human phenomena statement. All right, Buckingham Pie Theorem. So I came across this years ago when I was a graduate student. I thought, all right, I'll go and get the paper, because this is also a billion years ago, where a large portion of my PhD thesis was spent photocopying things. And like cards, you're getting money on them. You have to get your PI to give. It's just, and eventually you give up, and you've got a book and a journal, and you just put it down and you just go, boop, and you just. It's very much a struggle. Anyway, things are much better. At some point, I scanned all of these, so I think I'm not sure if my links are working. Are they working? No, they're not working. That's bad. All right, let me get PDFs of papers. Anyway, I'll show it to you. It's here locally. I know, thrillingly, look at this exciting usage. It's 1914, and I think I only have, yeah. So here's the scanned version. I don't know if I put that online anymore, but it's so here's the thing. So you go to a library, and often you're scanning something or you're photocopying something that may have been seen a little bit, but now and then you come across something that's been photocopied a lot, or it's been used a lot, and you're like, "Whoa, this is interesting, right?" There's evidence. It's like downloads now, right? So this was the downloads measure. There was one time at Columbia where navigate my way to the physics, I'm sure it's the physics library, and trying to find this thing. And eventually, you go through rows. Of course, nothing. It's insane. This is so insane. I mean, information lives in infinite dimensions or whatever, and we're in three-dimensional space putting it on. So I find the thing eventually. I go through it, and someone has torn it out. They've torn out the paper. They've just like torn the whole thing out. And I'm like, okay, I guess it's an interesting paper. It's terrible behavior. But some, various. I mean, we make the same sort of discoveries now because of downloads, or interactions online with things. But how much a book was used, or which sections of tables of logarithms were used, is sort of led to people making discoveries. All right. So anyway, so pretty beat up. Got the sticky tape on it, and so I photocopied it in a very gentle way. So what's this? So this is so you can see it's 1914. It's named after a person, so that's wrong. It's also the Pie Theorem, which is terrible. I mean, I think we should agree that pi, fine. Let's just use it for this one thing, the tau part aside. Anyway, occasionally you'll see people use pi for p, like probability, and it's a terribly confusing thing to do. Anyway, that's what's happening. So we have n-related quantities. There's some unknown equation that governs them, right? So we're in a world where we think equations apply. That might be true, not be really true for algorithmic stuff, but let's say that's true. So here's a simple thing, area of a square. So it's side length L, and we know this formula, and I know this is maybe going to be a little bit confusing, but let's say its area is L squared. So these are numbers, right? So this is 10 centimeters squared, and it's 100 centimeters squared. We're putting in numbers here. When I use these brackets, this is a notation, and of course these brackets are used to indicate lots of things, but in the dimensional space, it's used to mean what are the dimensions of this variable. And so this L is this, special L. It's like length, right? It's like this abstract notion, length. And length is a really fundamental piece, right? So, and then the dimension of this L measure, this little one, right, which again is some measured in centimeters or inches or whatever you want, is this capital L. So if you believe there's one equation, or that you're writing this down, you're interested in the area, and you know that you can measure the side length, you might say to yourself, well, there are only two variables in this equation, right? There's area and length. So if I make an equation, then I should be able to combine them in a way that I have to be able to, if there's really an equation that just works and is true, it doesn't matter how I measure things, right? It can't matter that I measure, use inches. So that's where you start to say, well, A divided by length squared must equal a constant, right? So this, right, a dimensionless constant. And then for a circle, we could say, okay, we measure R. And we know, we look at different circles. The only thing we know, there's R, right? There's just radius, right? That's everything. So if we want the area of this thing, area of a circle, then we'd say, well, if we divided that by its radius, that also has to be some constant. Because this is going to have dimensions length squared. This has dimensions length squared. They go away, right? So it's length squared over length squared. So these are very simple examples, but this is basically, this has to be a constant. The fact that it turns out to be 3.14, right? Like people struggle with that. Thousands of years, we figure it out. Turns out to be irrational. I mean, crazy things. So we can say this, right? We have a relationship, there's going to be P. We should be able to rewrite this thing, right? So there are n variables we're measuring. So in this case, we had area and length, but we might be measuring, speed, mass, some kind of length thing. There might be, the gravity might be involved, right? There are a bunch of things we say, matter in this system. The big difficulty is, of course, saying, enumerating all of the variables that matter. Okay, so Buckingham's story was, all right, well, we should be able to then say, we can't have an equation depend on anything we measure. It can't be the units of measurement. So if we have an equation, we have to be able to say, Okay, well, it has to be something like, another way of writing this is A of the circle. We have to have this. This must be true. And in this case, the same thing. There must be an equation. It can only depend on this dimensionless variable. We have to figure out what it is. And if we say, maybe we have 5 different units of measurement, right? There's time, there's mass, there's maybe something to do with light, lumens or whatever, et cetera, et cetera. And, we have these different measures. Maybe there's a power measure, so on. We have to be able to combine them to, with things like powers and it's just going to be powers and ratios like this. It's all it's going to be, such that the dimensions all get scrubbed off. So this is the right. So this is the example for just the square. It doesn't. We don't necessarily. We know this is the true equation, right? But we can at least say a over L squared equals some constant. And that would be our first dimensionless parameter, this pi1. And in this case, there's only one. And one of the games is, if you only have one dimensionless parameter, then it just has to be a constant. There's no way for it to vary, right? So that's a remarkable result. F equals ma. If you think you've got a system where you're talking about force and mass and acceleration, you could sit down and mess around with these things, and you know what force is, what its dimensions are, right? So it's going to be mass, length divided by time squared. Then you could start to say this sort of makes sense. Not that constants are a problem. All right, so these are sort of just loose little things. So you can get a long way with the back of an envelope. Now, envelopes are things that people used to use to send text messages, but you can sort of work with whatever you want these days. Yes, length dimensions. Who knows what a smoot is? So if you go to Google and say, I want, let's say, right, in smoots. So it's 100 meters is 58.76 smoots. So, smoot, there's just a bit of a ridiculous narrative that hit. So this was a hazing thing done at MIT in a fraternity where there was this guy called Smoot. It's a funny name, so that's fun. And they simply measured what's called the Harvard Bridge, I think, which is awful. The bridge that goes across to Boston from MIT. They measured the bridge in smoots. And then they counted it up and then put a marker in this, in 1 ear or something like that. I mean, hazy, but MIT style, I suppose. So Smoot. Yeah, so it's Oliver Smoot. Where's Oliver Smoot? So it was a right. There you go. So and they keep looking after it. So it's 364 smoots and plus or minus 1 ear. Very funny, guys. But Smoot became the head of the American National Standards Institute. So, I don't know if he came in and he said he really liked measurement and he talked about it all the time. They're like, okay, guy, we're gonna measure something with you. I'm not sure about that part, or if this was the defining moment in his life. Is like, I really want to measure stuff and I will own these people. I don't know what it is. Maybe not a movie, but it's close, right? Like there's a script here somewhere. Really funny. Yeah. And of course they made him, as you can imagine, he had to get up and be met, right? They had to do it properly, so he had to lie down and probably started CrossFit as well as a result. All right. Anyway, lots of funny things are units. Ooh. Maybe I have it in here. I think I have it, yeah. Okay, so let's have a platypus on we saw the platypus as a playful unit, right? So this makes sense, totally makes sense. So we've got a pendulum. We're going to imagine this is a rigid thing. It's not, of course. Platypuses are not rigid, but it's swinging back and forth. So if we think about this as the mass of a platypus, it's an idealized platypus pendulum situation. And you need, this takes some effort if you come to a new problem, right? course, and it's not going to work for everything. But I'm giving you a really profound way of understanding reality that has given us so much sort of leverage on things. The equations just need to be dimensionless, basically, is the story. And from that, you can kind of build a nice little thing. Okay, so, all right, swinging back and forth there. What's going on? Well, it's in a gravitational field. So there's G, there's the length, and there's a mass. And then there's the time, right? That's taking to go back and forth. And then we're not going to figure out the actual dynamics like a sinusoidal or whatever it is. We're not going to figure out some sort of, there's no differential equation that you solve and get the time dynamics out. But we can get, what we might hope to get is, right, this is just going back and forth. And we have this, we understood this a while ago, that pendulums run for a long time. And of course, if you make them really well, then, in a perfect setting, they'll just go back and forth. So there is a period here that you would maybe start to think is going to be related to the mass and the gravity and the length, right? And so if you add another platypus here, and you have maybe a collection of platypuses, maybe some baby ones, then that's going to increase the mass. What does that do? What's your intuition? Does it make it slow down or go faster? If you increase gravity, so there's more pull, the length gets longer. Which way does it dial these things? And it may be that they have, there's an L squared or a square root or something like that. These are the sort of things that pop out. Okay, so we've got 4 quantities, like I said. G's hanging around there, and the period tau. We'll call it tau. So this is this game, right? So we look at the dimensions. They're all pretty simple, right? They're very basic ones. There's time, length, and mass. And then acceleration is length divided, so this is a slight complication, right? Length divided by time squared. So Buckingham Pie Theorem, which I sort of flashed up in front of you, is we should be able to make, if this is, if there's really an equation, it shouldn't matter if we use Smoot's for this, right? Or whatever we use for the mass over here. None of those things should matter. So we should be able to construct an equation which has one or more of these dimensionless variables, right? So these, not variables, yes, dimensionless variables. So we're going, right, there's a length here, and the only other place is length here, right? So if you can play around with this in your head, you're like, okay, well, so it looks like we're going to have gravity divided by length somewhere. That has to be a construction, right? Because the only way to remove length from the dimension of length is to combine these two. The only way to combine time with something else is really gravity and time, right? So if we multiplied gravity by the G by tau squared, then that object would have the dimension of just length, because this would get wiped off. Right. And this is just fiddling around, and I'll try to show you a principled way to do it if you didn't. So gravity times tau, the dimensions of that would be, right, so length over time squared. And then you think, okay, well, I want tau squared, and then that would be, right, so that would be it. Okay, and so then we might say, well, there's a length, so let's also put in, I just called it L, curly L, which in LaTeX is L, very nice L. And then that would give us an L here, and that would cancel. So this would be right, there'd be, the dimensions of this would be just the dimensions of a number. So that's one object. So this is one, so we could say this is pi 1. This is a variable. This has to be, right, so now we're building this function, pi 2, I just can't believe there are pi's, pi 3, right, in principle, right, so we'd stick this one here. We could say, okay, whatever equation there is that tells us, that relates the, sorry about that, whatever equation, connects these things together, if such a thing exists, it's going to have this blob in it somewhere. It could be sine of this thing, whatever, log, right? It could be something, and it could appear in 4 different places, but that blob, that thing has to stay together because it's the only way, and we're just, there aren't many variables here. It's the only way to get rid of length and time and so on. So what about mass? I can't hear anything, so that's a problem.
It's independent of mass.
Yeah, so it's got to be independent of mass. There's no way mass doesn't appear in any other thing. It's kind of surprising, right? You sort of think, we get a little confused about gravity. This is just an acceleration, right? It's not hanging around anywhere else. So in fact, that's it. This is all we have in this case, because the only way to have mass, the dimensions of mass be 1, is this. Raise it, it can't be in there, right? So, right, power of 0. So then we could think, okay, so we'd have a whole thing which is d squared L mass to the 0. This whole thing, which is a 1, there's only one of them, so that has to be a constant. And from there, you can say, okay, gravity's fixed, right? That's some number. And then basically this gives you that tau is proportional to length to the power of a half. So that's pretty cool, which is true, actually.
Now, there's a downward limit on that, though, because at a certain point, what the growth wave figures into it.
Yeah. So this is assuming a perfect platypus pendulum. And, right, so that it's a point platypus at the end. This is a rigid thing, no friction. Yeah. So that's a very good point. Like when you start to have little other pieces that start to matter, then this explodes. Yeah. Or gets tricky. Yeah. But even when there's some, reality creeps into this thing, it's still, it doesn't depart from it immediately, shall we say. It doesn't. There are some things where having some hidden dimensions is a bad, breaks the whole thing apart. But in this case, it would be corrections. Yeah. So you'd have this plus corrections. If you wanted to set, because we release it, we've specified mass, we've specified length, gravity specified, tau is an output. We want to see what the period is as a result. Yeah. So that's, this is just messing around. We did it with an envelope story here. But here's a little formalism for how you would actually do it, right? And it's a good example just to play around with. So linear algebra time. So what do you think? Yeah? Yeah. All right. So now we're going to say, let's make it a little more fancy. So we can attack problems in general. We'll say, okay, these are the variables we start with, like mass, length, gravity, and the period. So that's where they sit. And then we want to construct the dimensionless quantity, all the dimensionless quantities that are there, right? So there are n variables, and then there'll be p of these. And in general, there are less. I mean, we could have started with, say, mass and length, and then there are just that's it, right? We have a system that has, which is a bit of a funny thing, but we could, Anyway, the point is we're going to start combining them, and that will generally reduce the number of variables we have. And of course, we're trying to make only dimensionless ones. So the game is this. We're going to say, let's just think of the ith one. It's going to be some power of the first variable, right? Because this is what we've done. We've got g to the power of 1, L to the power of -1. This is tau to the power of 2, and then there was a mass to the power of 0, right? So this is a general expression. So, right? And we really want to find all the powers, right? So we want to find it such that these powers, if we put in the dimensions of these units, like gravity, for example, could be here, and it would be length over time squared. So we want to put in the actual dimensions, and we want the dimension of this to be 0. So again, this is using this dimension operator, right? So we want the dimension of the ith dimensionless quantity. We're going to say, well, it's the dimension of whatever the first one is, right? So this could be gravity, this could be mass, this could be the length one, could be power, could be lots of different things, right? And we're going to raise them all to these powers. And then we want them basically to sum to 0. Okay, so we have this before. So these are the dimensionless pieces. And the 3 dimensions in this system are just length, mass, and time. That's it, right? We don't have anything else. Okay, so we would do this, for example. We'd say, okay, the dimension of this sort of general mixture of these things, and we'll do the length. I think it's length, mass, gravity, and time, right? That's the variable length. That's its dimension. Mass, that's its dimension. Gravity, that's its dimension. And time, that's its dimension. And we're trying to raise these things to these powers x1, x2, x3, x4. Okay. So we're going to restructure it. So if you look at this, we're going to have L. There's an L here, and just as we sort of argued, there's an L to the x3. So there's L to the x1 plus x3. Mass is by itself, and then time is going to pick up a minus 2x3, that's this piece, plus x4. So just a little bit of algebra, and now what you want is this has to be 0, this has to be 0, and this has to be 0. Because then there will be L to the 0, mass to 0, time to 0, and the dimension of this object will be 0. And so there may be, in principle, there may be, this is a big system, there might be 5 ways to do this. And so we'll write them out as equations. That one should be equal 0 at the end. What are we talking about now? What is this? What is this part of mathematics? What are we messing around with now? x1, x2, x3, x4. We have linear combinations of them. So you could do basically what we did over here, right? You could do these simultaneous equations type things, but this is linear algebra, right? We're in linear algebra space, and or matrixology, as I prefer to call it. Terrible branding. And so we can write it like this. So we can write it as a null space equation, right? So this is the first equation. It's x1 plus x3 equals 0. The next one was just x2 equals 0. And then the third one was minus 2x3 plus x4 equals 0. So this is ax equals 0, which is to your delight, I'm sure. In this case, these are the standard thing. So this is a horrible collisions, but in this case, it's just a matrix notation. That's it. Yeah. So it's a null space problem. This is the indicator matrix. Vectors. It's not actually how I write it on a blackboard is different. That's more like it will be ax equals 0. Yes, very nice. So the number of dimensionless parameters in general is going to be the rank of null space, which is n, right? So n is, m is 3. It's a row, 3 rows, 4 columns, and the 4 columns minus the rank of the matrix. 4 minus the rank of the matrix is going to be the dimension of null space, and that's going to be the number of dimensionless parameters. So this is a bit of an odd thing, right? We've gone from this Buckingham Pie Theorem, we march through it, and it comes out, what's the dimension of null space? Right, so this is some matrix. What's the dimension of the space of vectors that it sends to 0, right? So this is, what does it crunch to 0? And this is something that's taking 4 dimensions to 3 dimensions, so it's at least 1, right? Because it's trying to take a 4-dimensional space and squish it into a box in 3 dimensions. And that could be a 2-dimensional subspace or a 1-dimensional subspace, or the whole of 3 dimensions. So n is 4 here, and the rank is 3, right? You can see this is a rank 3 matrix. And so we must have this case. We just have one dimensionless variable, which, you go through and you solve this problem, and essentially, and you will get out this same beast. You only get one solution, and it's, of course, it's right any power of this, right? You can have any power of this. That doesn't matter. But we usually just, right? We could have written this as, I mean, we did end up with tau is proportional to L to the half. So this could be L to the half, G to the half, tau, just as you might prefer. But it would be silly to have, G to the 100, tau to the 200. Right.
Why do you have the line above the A when you're at the board? On the side of the A?
This thing? Yeah, that's just when you end up with a board full of, this is blackboard notation, right? Just when you end up with a board full of things, you know which one's a matrix and which one's a vector. Terrible things happen. It's a preference. It's a preference, yeah. And I like doing it, so that's also true. So pi1 is a constant, and so, but the general game is we're going to create a matrix A. Yeah, well, that's a little much to say. That doesn't. I don't think that helps you to say that. I mean, the construction is the way to do it. This is true, all true. But the construction is the way to do it, right? So this one, getting to here, getting out these equations, and then just putting it into a null space problem. So this is fine. We could do this by hand, but if you have a much bigger system, maybe not so great. Okay, so that's good. And so you would find this, right, as we did. But the idea is just to find it properly through here. Okay, good.
So that's sort of like distilling a system with units into a metaphor that can then be brought somewhere else. Is that what you did here?
Well, it's just, I mean, it starts from the premise that you must, if there's some true equation of the universe sort of situation, it can't depend on the units of measurement. And so you simply work, everything just follows from that. You might, this might be an ugly object, right? This is not necessarily, when you look at it, sometimes these variables will have a meaning, right? Like this is the X of a system or something, right? But sometimes you've just made, because we could turn that upside down, it's still a constant. So there may be some arrangement of it which has a better physical story for itself. And so so we just did it for like a hypothetical pendulum. So Taylor was a famous fluid mechanics character in England. And there was this was on the cover of Time magazine in 1945, and it's one of the Trinity tests. Of course, nuclear hydrogen bombs. I mean, it's a grave moment in human history, and so they're blowing up the New Mexico desert and then taking photos of it. And this was I think the front cover, and they put the time here, right? So there's the blast radius, and it gets more and more messed up. And they tried to sort of tell people, I suppose. I mean, obviously, Time magazine, they're not hiding this, but there's the Empire State Building, and this is fairly, this is 0.006, 9 seconds. So there's and then scale, 100 meters, right? So what was certainly not talked about was how much energy there was, right? That's a secret. So Taylor's sitting, I think, at the breakfast table and figures this out on a piece of paper, because he realized that you had, and in terms of these sort of Buckingham Pie things, is a very famous story. Well, there was a scale, right? So this thing. So you're thinking about this thing growing. So what do we need to know about how it grows? Well, there's time. There's the size of it, which is the radius, and then he just thought, well, density of air is going to matter because it's pushing against that. There's the energy that it starts with. And so these are still the same game, right? There's mass, length, and time. We don't often go beyond those. And then, but it's 4 variables in 3 dimensions. So it's a kind of same as the pendulum story. So there's a chance that it actually gets really reduced. And if you play around with it, you don't have to do the matrix thing, of course, but it's a nice practice, I suppose. Then if you rearrange things, then you get this, which is not obvious, right? But the energy is going to scale as the density of air, which is a benign thing, but then r to the power of 5 over t squared. So he was able to then play around with that and figure out, and then get an estimate for how much energy was in this bomb, which is, supposed to be a absolutely top secret. But it was, in a sense, on the front of Time magazine. If you read it in the right way, shall we say. Yeah. Yeah. So I listen to a lot of podcasts. Radiolab, I don't really listen to much anymore, but there's some really great ones in the past, and I still have them. I don't know. But this is on the Cold War. This is the dating of cell age because a lot of people ended up with some radiation in them. So, the experiments we accidentally make. Interesting piece. So the base units, you'd think this was sorted out. I remember sort of coming across this maybe 10 years ago and being kind of really surprised by this. But there was just a lot of, it was very unsettled actually about what the base units were and how they were being measured. And so now we have the kilogram for only until recently, there was a kilogram in France, which was the kilogram, right? And it had to be copied and so on and replicated. That was the standard, which is not a great bit of work for us scientifically. Like, there's a bit of a worry. It's like, where's the kilogram? I've lost it or something or whatever, But what they did do is cleaned it at some point and they messed it up, right? They took off like a grain of sand essentially, and then then you're in trouble, right? So, these things do matter. So now it's an artifact. So now it's been changed. So we're going to sort of do these funny things where we specify Planck's constant, like this is good enough, and then say, oh, if you measure a bunch of things, that will be seconds or whatever, right? So there's and the meter has been changed as well to fix the speed of light in this way. I guess the point is it doesn't matter, right, for errors, but it's an odd business. Anyway, there's another Radiolab piece here, and it's quite charming, actually, I suppose. Yeah, now this was a problem. So this was initially what we had. The kilogram was a real thing, and we had to know that to measure, these other pieces, and then it's been changed so that there are these fundamental pieces outside of it. Okay, turbulence I'll mention quickly. This is another just part of physics. There are a lot. Oh yes. So Louis Fry Richardson, we'll come back to, studied the scaling of deaths in wars. Extraordinary character. There's a Richardson number, so there's a number named after him in fluid mechanics, and sort of predicted meteorology being run by computers, talking about all these people solving differential equations in a room. And but he also did some work on the scaling stuff. It's on the statistics of deadly quarrels, which includes the First World War, which is a quarrel of sorts, right? Anyway, so turbulence is a famous edge of fluid mechanics kind of problem. Obviously matters tremendously, but the equations kind of break down. This is just a little extra bit. This is people get excited about turbulence. So this is a claim that Van Gogh's papers had have a sort of a turbulent type measure in them that, or sort of there's a way to measure turbulence, I suppose, about the colors that is, and it seems to be that it's when it's not really in other famous painters apparently, and it's not when he was stable. So I don't know. Anyway, a little bit of fun, but this is the real story. So Kolmogorov, who sort of giant brain human. That should be fixed. But this same sort of thing, same kind of game, figured out that the energy in the energy spectrum function for turbulence should kind of have this behavior. Okay, right. I'll have to. Okay, all right. Anyway, so I'll just quickly say this is a whole thing, but energy. there's energy distributed across all modes, um, blah, 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 and then there's no real internal characteristic. And that's sort of reminiscent of that, those quotes at the start from Lewis Fry Richardson and so on, that it has a fractal behavior. So this is just a back of the envelope thing. It actually holds up well in experiments, but it's been a really tough area for fluid mechanics people. Then, of course, we have geometry of nature. So this is Benoit, this is Mandelbrot, this is Brocky flower, one of those things. So, how do you actually, so how do self-similar geometries form? Of course, we're sitting here with a number of them, right? Our blood networks are self-similar structures. All sorts of things get produced in nature in that way. Trees, of course. And going back in time, and this is work that I spent, back in time for me too. My PhD was a fair amount on branching networks in general, and river networks has this great history of being studied in that way, and it's the first place anyone kind of quantified self-similarity in what would be called fractals later on. Yeah, roughness of time series, that's the stuff that financial people, of course, well, not academics, I suppose, are interested in. Richardson, here he pops up again. He's the one that measured, what is the, Mandelbrot did this too, but basically what was the length of the English coastline, right? How do you measure that? And it depended on the ruler, right? And so that was an observation at the time. And then Benoit B. Mandelbrot pops up and gives them a name and a lot of work. There was definitely a lot of work where there's a lot of mathematical objects that were fractals, which is fun. Of course, the Mandelbrot set, but there was a bit of a disconnect with reality, right? With actually coming up with mechanisms that, why is the coastline fractal? Like, what's happening mechanistically that produces it? So that's fine. I mean, a fair amount of it was measurement of reality. You've got to do that. But getting the mechanism that, explaining why they come about, that's hard. Okay. Oh yeah, fractal diet. Yep. Okay. All right. So this is a good. I wanted to get to this. So this is moving out of the physics space, and that was a bit of a collision between physics and biology at the end. So this is into people. So this is Luis Betancourt, who was at the Santa Fe Institute, is now at Chicago, and he really, I think, did good database work at the time, when it was still being kind of looked down upon. Because we got to a bit of a stage where everyone's like, oh, I want to explain the world, but they stopped looking at the world, which is dangerous, right? So this was, it has this lofty title. So the pace of life in cities is that terrible graph that I showed you at the front. They actually put in the heading, in the title of this thing. Anyway, but they went through and said, all right, well, just as a function of city size, and what's a city? That's a little bit of a contentious thing. What is Boston, the blob in the middle, or is it 5 million people? So there's people do good and bad things. With respect to that, there's sort of the functional organism. What is Tokyo? But measured things like infrastructure, like just roads and telephone cable, that sort of stuff, right? Wealth. Which of course, there's average wealth, there's median wealth, but wealth has this power, this very skewed distribution. So you'd have to think about that as well. Crime levels, all these sorts of things, and looked at it as a function of city size. And this didn't seem to have anything to do with, I think, in the original paper, maybe not so much density, right? Which is a bit odd. And if you look at, I have some work I never published, but if you look at population and the area subtended by a city on a log scale, then, right, so populations of cities, you go from towns up to big cities, whatever, Tokyo's maybe, it depends how you measure it, 40 million. Then the area varies by 2 orders of magnitude, right? This is a really huge diversity in what a city of people can subtend, like how big that space can be. Anyway, so diversity, you would think density would matter. You'd think it would matter, but that's not what they seem to have at the start. So this is this dodgy one, right? So the scales are all varying here. The natural log, it's a mess. That's the walking one. but this is wages. This is some measure of wages. You have to look, go and look at what they are. This is supposedly super creatives, which is another funny measure. Things like patents is one kind of way of trying to measure that, right? And this one is, so this is heart rate. So this is because of Jeff West and is really unnecessary. Okay, so what you see is these scalings are close to 1, but a little bit above, right? So this is, I would say just ignore these ones, but these are a bit above, and this was their big claim, that they're like 1.1 to 1.2, like, so it is a bit bigger. So as you go up in population, there is this. It's not just double the population, double the total wealth, or whatever it is. It's actually increasing in this. The social things are increasing, and so this is their claim. So there's sort of a break. There should be sort of a line here and a line here. So these things up here are social. They have some social aspect to them. And here's the scaling law exponent as a function of population size. Whatever these measures are, these are all a bit above 1. And they're going to say, they're actually going to say 7.6, but whatever. They're floating around. Here are the errors. Of course, we've seen a couple of plots, but all these plots are hidden. It's for the US, some from China, some from Germany. It's a variation. So, patents, inventors, they're not really ordered by, how are they ordered? Huh. I think they just ordered this. They're not really ordered by fit. Anyway, so these things, so it's a mixture. Some of these are like good things, you would think, like patents and inventors, maybe, wages, right? So there are benefits to being in a bigger city, GDP, but then there's a couple of measures of disease and crimes, right? So, and crime rate. So these things are going up. There are then some elements which seem to grow in a per capita kind of way, right? So these are just houses which make sense, employment, right? These things don't have a way of scaling. Even electrical consumption, water consumption, and then there is some things where you get a return to, like you get a benefit from being in a city. So there are less of, and of course, there are only 4 things, but road surface, that's a hard thing to measure. Electrical cables. So these are, you think of as being good things, maybe. Yeah. All right. So that was an initial paper. It's in PNAS in 2007. There's been work done since then, and there's a whole setup at Chicago around this. My old friend Neil Brenner, who's an urban Marxist geographer, is part of it. So I'm sure they have some interesting discussions. But yeah, this was a big deal at the time, and I think it's interesting to kind of reflect on it. But these are just a summary, right? So the global supply type things, making the system run, cables and so on, and roads seem to scale sublinearly. Individual costs are scaling linearly, and then these social ones are scaling superlinear. That's the big claim. And then, as I said, density doesn't seem to matter. And measuring what a city is difficult. But these are sort of potentially gigantic results. And then you say, well, why don't we just build bigger and bigger cities? That's a complicated thing, right? And of course, now we've hit a time where remote existence is becoming more and more possible, certainly for large portions of the industry. So the working population. So we'll see what happens with that. Okay, I'll end with this one. So this is it's Betancourt again. It's a couple of years later, and what they're going to do is say, okay, now we've got these scalings. It's like we did for the weightlifters, right? Let's just subtract that scaling out, and then look at which cities, big or small, right? You've figured out, like you've normalized properly for their sizes instead of just dividing by their population. You've divided by the scaling law, which cities are sort of punching above and below their weights. So it's looking at residuals again, right? So does a city have more or less crime when we sort of normalize by population, but in this scaling way, allometrically? Yeah. Okay. All right. So, yeah. So this is interesting. There's a couple I'll show you here. So this is income. The first one is, yeah, it's a GDP type thing, but a metropolitan product, and so on. And then these are residuals. This is just all sorts of stuff like do they behave, blah, blah, blah. And then, so here's an example where they've been subtracted and then ordered. And so Burlington at this time was number 2. So this is a good thing. Like, so that, right? So these are cities that are producing more patents when normalized properly, right? Divided by n to some power of like 1.2 or something like that. And then, the team goes away here. So, this is a very interesting, this is a way you want to, well, you have to believe the scaling is reasonable and so on, that you've actually measured things well. But then, big stories. Like now we can justifiably kind of compare all these cities at the same level, and then you can start to see, this is a mixture of places, right, in terms of size, mixture in places in terms of size. So who's doing well? It does not just, of course, the biggest cities have the most patents, right? But this is a way of figuring out exactly what's going on. Okay, it's a good place to stop. The last thing to say is there's a paper in Science a few years after it where he has an argument, Betancourt, that it's a 6, right? So it's 1 plus a 6, 1 minus a 6 for all those scalings. I don't know. All right, we will talk more on Thursday, and I'll sort out the office hours things. Yes.